Okay. Let's see. This is section 11.1. We've been talking about graphs. Now we're going to talk about trees. So trees are a specific type of graph. Let's begin with the definition, and then we'll look at a few examples. So first, a tree is an undirected graph that's connected, first of all. Remember, that means that it has one connected component, and that there exists a path, at least one path, between any two vertices. So we have a undirected connected graph with no simple circuits. Now, simple circuits were defined back in section 10.4. I didn't really talk about them much in the notes, but a simple circuit is just the same as a cycle subgraph. Now, I did explain subgraphs, so the idea would be there's some subgraph that would form a cycle of any length. That's what a simple circuit is. So let's look at a few examples. Here are some graphs that are similar. The first two are similar, and the second two are similar. This first graph here is a tree. And we know it just because it doesn't have any circuits in it. I can form any circuits, any cycles at all in here. But this second graph here, whoops, excuse me, just grabbing a pen. I can form a circuit there of length 3. So that means this is not a tree. This one over here, let's see. If I trace around, it looks like, I don't seem to have any cycles here, right? So this is a tree. However, that same graph with one extra edge included on the end here forms a cycle, like so. It's a little 4 cycle right there. So that one is not a tree. So that's the basic definition. Now, I think the reason they're called trees is because you can kind of arrange them. You could arrange the graph so that it looks like a tree, so that it's going up. And you know how trees branch out, but then those branches never come back together again, right? Trees don't grow that way. Branches split, but then they don't rejoin. So that's I think why they're called trees. There's a theorem about trees we're going to start with, and I'm going to show you a proof of this theorem. Just mainly as an example of what proofs kind of look like, how you can write proofs involving trees. I've asked you to prove something on the assessment, and so I think this will help you a little bit with proving things on your own. So the theorem is that an undirected graph is a tree if and only if, given any two vertices in that graph, there will exist a unique path between those vertices. So we know that if it's a tree, it's going to be connected, which will mean a path will exist. But what we're saying here is that path is unique, and that is both a necessary and sufficient condition for an undirected graph to be a tree. Okay, so I'm going to scoot my papers up here a little bit. All right, I'm going to stick the theorem at the top there. And then what I'm going to do is bring in my proof. And rather than write this proof exhaustively, I'm going to kind of reveal it gradually and explain it as I go. So just checking to make sure everything looks okay. All right, so here's the proof. So first step in the proof is going to be to let G be a graph, okay, an undirected graph. And the vertex set and the edge set are named so that we can refer to those if necessary later on. Okay, so now because this theorem is an if and only if theorem, right? There's two propositions here, and they are meant to imply one another. Remember, if and only if here means is that double arrow, and it's equivalent to like arrow implies one direction and implies the other direction. So we're going to prove the if and only if by doing one direction at a time. So first I'm going to do the forwards arrow, starting with our assumption that G is a tree. This means, remember, that it is connected and contains no circuits. All right, so using that as our starting assumption, now our goal is to prove that any two vertices, there will be a unique path between them. So our next step is to let A and B just be two arbitrary elements of our vertex set. So I'm working with arbitrary elements so that I can show that what is true about A and B is true for any two vertices. All right, so now, since G is connected, I can guarantee that there will exist a path from A to B. All right, I'm going to rearrange my papers here for a moment, scoot this up slightly, and go ahead and, oops, decide where to put this down. All right, I'm going to go ahead and start drawing a little diagram on the side over here. Let's have our vertex A and our vertex B. And what we're saying is, since our G is connected, we know that there will exist some path from A to B. So I'm going to draw a path. And I'm not going to bother naming any of those vertices, but there's a path from A to B. All right? So now, we want to show that that path is unique. And to prove uniqueness, there's a general strategy that I taught you back in chapter 1, which is to assume that it's not unique. Assume that there is another one of these things, whatever they are, which is distinct from the first. And then try to find a contradiction in that. And that would show that, that the one has to be unique. So we're going to suppose, seeking contradiction, that there is a second path distinct from the first. So I'm going to draw a second path in this diagram, which is different from the first path. So let's have it go, let's have it start by going to the same two vertices, same vertex over here, but then I'm going to have it branch off and go a different direction, and then kind of do something like that. Okay, so there we go. So now I have more than one path that I could take to get from between A and B. All right, I think you can already probably see that there is going to be a problem with this. So what we can do is say, by combining the first path with the second, rather the reverse of the second, so we're taking the first path and then taking the reverse of the second, meaning I'm taking the vertices of the second path in the reverse order. By combining those together into a single path, we obtain a circuit, a path that begins and ends at the same vertex. That existence of a circuit contradicts our original assumption that G was a tree. And so therefore, the path from A to B must exist and also must be unique. So that's the first half of the proof. I'm going to go ahead and prepare the second half here. And I'm going to bring back the theorem for a moment so we can look at what it is we need to prove in the second half. Okay, that looks fine. So remember the theorem, the if and only if, we've already proved the forwards direction, so now we have to prove the backwards direction, which means we're going to start by assuming that that given any two vertices, A and B, there is a unique path from A to B, that it exists and it's the only one. So we're assuming our second statement. Now we're going to prove that our graph is a tree. Okay. So here we go. Kind of like last time, we're going to assume seeking contradiction. We're going to assume seeking contradiction that G has a circuit. Okay, if we can prove that G doesn't have a circuit, then we will have shown that it is a tree. So I'm going to start drawing a little diagram again. Somewhere in our graph is a circuit, which is a subgraph which forms a cycle. So it doesn't, I mean, we don't know how long it is, so it looks like I made one that's 6 cycle, but whatever. It's just kind of a representation of what's going on here. So we have a circuit. So now, if A and B are two vertices in that circuit, let's say A is over here and B is over here, then we can form two distinct paths between A and B by going in different directions around the circuit. So you see we can go this way, or we can go the other way. Swap out, do a different color, and form two distinct paths between A and B. But that contradicts our assumption that paths between vertices must be unique. So that's also a contradiction. that shows that a circuit can't exist in this graph, and therefore G is a tree. So, thus, we can wrap that all up now that we've done both directions and say, thus, G is a tree if and only if paths between vertices both exist and are unique. Here we go.